What if darkness creates more than it conceals? We often think of the cosmos as a spectacle of light, a brilliant show of stars and galaxies. But what if the true architect of the universe is not the light we see, but the profound darkness we overlook? Imagine a sculptor who creates masterpieces not by adding clay, but by carving away stone. In a similar way, the deepest voids of space may be actively shaping everything we observe. This idea turns our traditional understanding of cosmic evolution completely on its head. Darkness is not merely empty space. It is a dynamic participant in the design of the universe. Throughout this journey, we will uncover how scientific theories, historical insights, and modern research all point toward a stunning paradigm shift. You will gain a completely new way of seeing the cosmos, one where absence holds more creative power than presence. How did ancient cultures perceive the void long before telescopes existed? What invisible forces are currently weaving the fabric of reality in the dark? Are you ready to see the universe not for what shines, but for what shapes from the shadows? Long before we had telescopes to peer into the void, ancient cultures saw the darkness not as an absence, but as a presence. In the creation myths of many civilizations, darkness was the primordial womb from which all existence emerged. The ancient Egyptians revered the god Amun, who embodied the hidden darkness of the primordial waters, the essential nothingness that preceded the first dawn. For them, and for many others, the dark was not empty. It was potent, alive, and divine. It was the first thing that ever was. This view stands in stark contrast to our modern, often simplistic, notion of darkness as a mere blank space waiting for light to fill it. Our ancestors understood something profound, something we are only now beginning to rediscover with our advanced instruments. They sensed that the dark held a creative power all its own. This philosophical struggle continued with the great thinkers of ancient Greece. Aristotle famously put forth the idea of horror vacui, nature's abhorrence of a vacuum. He argued that empty space was a logical impossibility, that nature would always rush in to fill any void. This belief, that true nothingness could not exist, held sway for nearly 2,000 years. Medieval scholars fiercely debated this very point, questioning whether the heavens themselves could contain a true void or if they were filled with an invisible substance, a crystalline sphere or an ethereal medium. The debate was not about emptiness, but about the nature of reality itself. Was the cosmos full, or could it contain absolute nothingness? The scientific revolution began to shift this perspective, but not entirely. Johannes Kepler, in the early 17th century, meticulously described the laws of optics and how light behaves. Yet even he could not escape the puzzle of the dark. He pondered why, if the universe was infinite and filled with an endless number of stars, the night sky was not a solid, blinding sheet of light. This question, known as Olbers' paradox, would haunt scientists for centuries. In the 19th century, physicists like Lord Kelvin wrestled with it directly. They calculated that in a static, infinite universe, every line of sight should eventually end on the surface of a star, making the night sky as bright as the surface of the sun. The fact that it is dark, that we are surrounded by blackness, was a profound cosmic mystery. It suggested something was terribly wrong with our understanding of the universe. These historical voices, from priests to physicists, show us that the enigma of darkness is not a new frontier. It is one of the oldest puzzles we have ever faced. Our current investigations into dark matter and dark energy are not a sudden break from the past. They are the latest chapter in a long, enduring conversation about what the dark really is, and what role it plays in the grand design. This centuries-long inquiry has set the stage for a revelation far stranger than anyone could have imagined. The solution to Olbers' paradox arrived with a startling revelation: the universe is not static. It is expanding. This expansion stretches the light from distant stars, shifting it into the invisible infrared and making the sky between them appear dark. But this answer only solved one mystery by revealing a far deeper one. What if the darkness between the stars is not a passive backdrop, but is itself a dynamic and creative force? This brings us to the strange physics of absence, to the quantum vacuum. What we perceive as empty space is anything but empty. According to quantum field theory, the void is a seething, bubbling sea of potential. It all begins with the Heisenberg uncertainty principle, a fundamental rule of the quantum world. This principle states that for extremely brief moments, energy can appear from nowhere, as long as it disappears again almost instantly. This is not a violation of physics. It is a feature of reality at its smallest scales. This energy loan allows for something astonishing. Particles and their antiparticles can spontaneously pop into existence, borrowing energy from the vacuum for a fleeting moment before they collide and vanish back into nothingness. These are called virtual particles, and their constant, frantic dance is known as vacuum fluctuation. Imagine the deepest, calmest ocean you can possibly picture. From the surface, it looks perfectly still and empty. But just beneath that serene surface exists a world of incredible turbulence, with currents swirling and creatures darting in and out of existence. The quantum vacuum is that ocean, or think of a completely silent room. We perceive it as empty of sound, but in truth, the air in that room is filled with vibrations at frequencies our ears cannot hear. The vacuum of space is that silent room, humming with an energy we are only just learning to detect. This concept of a vibrant void has a fascinating history. The physicist Paul Dirac first conceptualized what he called the Dirac Sea, a vast, invisible ocean of negative energy from which particles could emerge. While his specific model has evolved, the core idea was revolutionary. Darkness is not empty. Modern quantum electrodynamics has calculated the energy density of this quantum vacuum, and the numbers are beyond staggering. They are almost unbelievable. The energy in a single cubic meter of so-called empty space is enough to boil all the oceans of Earth. This is not a metaphor. It is a theoretical calculation that highlights the immense, hidden power latent within the dark. This quantum vacuum is not just a curious sideshow. It is the fundamental backdrop against which all matter manifests. Every star, every planet, every one of us exists within this energetic medium. It suggests that the darkness we see is fundamentally creative, not passive. It is a reservoir of infinite potential, a canvas upon which the universe paints with light and matter. This understanding of the quantum vacuum gives us the first mechanical clue, a tangible process for how darkness could actively participate in shaping the cosmos. This invisible architecture was first glimpsed not in a grand telescope's view, but in the stubborn, inexplicable motion of stars within galaxies. Astronomer Vera Rubin was meticulously measuring the rotation curves of spiral galaxies, expecting to see stars at the outer edges moving slower than those near the bright center, just as planets farther from the Sun orbit more slowly. But the data told a different story, a story of a hidden hand. Stars at the very outskirts of galaxies were whipping around just as fast as those near the core. This was impossible according to the laws of gravity and the amount of visible matter. The only explanation was that each galaxy was embedded within a massive, invisible halo of something else. Something that did not emit or absorb light, but exerted a tremendous gravitational pull. This something is what we now call dark matter. We now understand that dark matter makes up roughly 27% of the entire mass energy content of the universe. It is the universe's dominant form of matter, outnumbering the atoms that make up our world by a factor of about 5 to 1. But its power lies not in its abundance, but in its nature. Because dark matter does not interact with light or electromagnetic forces, It is free from the complicated pressures and collisions that affect normal matter. This darkness is its greatest strength. While ordinary matter, made of protons, neutrons, and electrons, can scatter, slow down, and get stuck, dark matter simply streams through itself and everything else, governed only by gravity. This allows dark matter to act as the universe's master sculptor. In the early cosmos, slight density, fluctuations in the dark matter began to collapse under their own gravity, forming vast gravitational wells. Think of these wells not as pits, but as templates, as invisible molds. Ordinary matter, the gas that would become stars and galaxies, was then pulled into these pre-existing dark matter scaffolds. This process crafted the cosmic web, the largest structure in the universe, a magnificent lattice of dark matter filaments connecting immense galaxy clusters and surrounding breathtakingly empty voids. Supercomputer simulations show this process in stunning detail, revealing how the universe's luminous architecture is literally drawn in the negative space defined by dark matter's unseen hand. Theoretical physicists like Dr. Lisa Randall have proposed that dark matter's role may be even more complex and creative. She and others have explored the possibility that dark matter might have its own rich physics, perhaps interacting through forces beyond gravity that we have not yet discovered. This opens up a fascinating idea, that the dark sector could host an entire shadow universe with its own intricate rules, a hidden landscape that subtly guides the formation of the visible one we inhabit. The profound takeaway is that the darkness of dark matter is not a flaw or a missing piece. It is the essential feature that allows it to shape the cosmos. If it shone like a star, it would be subject to the same chaotic forces and could never form the stable, gravitational framework upon which everything is built. Its absence of light is precisely what grants it the power to create light's home. But if dark matter provides the hidden mass, what provides the hidden energy? The force that seems to be stretching the very fabric of the cosmos apart at an ever-increasing rate. The universe's expansion is not just continuing, it is speeding up. This startling discovery in 1998 overturned a fundamental assumption held by nearly every cosmologist. Two independent teams were measuring the distances to incredibly far-away supernovae, using them as cosmic mile markers. They expected to find that the expansion of the universe was slowing down, gradually braked by the collective gravity of all matter. Instead, they found the opposite. The supernovae were much dimmer than they should have been, meaning they were much farther away than anyone predicted. The only possible explanation was that the expansion of space itself was accelerating. Something was actively pushing the galaxies apart, and that something is what we now call dark energy. This mysterious force is the dominant component of our reality, making up about 68% of the entire universe. It behaves not like matter, but like a property of space itself, a kind of negative pressure that causes spacetime to stretch at an ever-increasing rate. This concept has a fascinating historical footnote. Albert Einstein himself had inserted a term into his equations of general relativity called the cosmological constant, a fudge factor meant to keep the universe static, which was the prevailing belief at the time. He later called this his greatest blunder when the expansion of the universe was discovered. Yet, in a stunning twist of fate, his so-called blunder may have been prophetic, as the cosmological constant is the leading candidate for what dark energy actually is. To visualize this accelerating expansion, picture a loaf of raisin bread rising in the oven. The dough represents the fabric of space. The raisins are galaxy clusters. As the dough expands, every raisin moves away from every other raisin. The bigger the loaf gets, the faster the raisins separate, not because they are moving through the dough, but because the dough itself is stretching. Now, imagine the oven is on a magical setting that makes the dough rise faster and faster over time. The gaps between the raisins grow immense, creating vast stretches of empty dough. In our universe, Dark energy is that magical heat, and the voids between galaxy clusters are those growing expanses of emptiness. This is not a passive process. The relentless push of dark energy actively creates the largest structures in the cosmos, the cosmic voids. These are not mere accidents or blank spots. They are dynamic regions whose growing emptiness governs the fate of everything around them. As these voids expand, they pull matter away from the delicate filaments of the cosmic web, effectively starving the regions where galaxies form. The darkness is not just spreading. It is actively sculpting the universe on the grandest scale by determining what structures can and cannot survive. Current projects like the Dark Energy Survey are trying to measure the precise effects of this force across cosmic time. Is the strength of dark energy constant, as Einstein's cosmological constant suggests, or does it change, perhaps growing stronger or weaker? The answer will determine the ultimate fate of all cosmic structure, deciding whether the universe will end in a cold, dark silence or tear itself apart in a big rip. This research reveals a profound truth. The pervasive darkness of expanding space is not a void in the sense of nothingness. It is an active, shaping presence, the dominant force writing the final chapters of our cosmic story. These cosmic voids and the accelerating expansion they represent are the largest expression of darkness as a creative force. But this same principle of creative darkness operates on a much smaller, more intimate scale, within the very clouds where stars are born. The birth of a star is not a bright, violent explosion. It is a quiet, hidden process that can only occur in the deepest dark. This process unfolds within vast molecular clouds, often called dark nebulae. These are not empty spaces, but incredibly dense regions of gas and dust, so thick that they block all visible light from the stars behind them. From our perspective, they appear as black silhouettes against the glowing backdrop of the Milky Way, cosmic ink blots on a starry canvas. But these apparent voids are anything but empty. They are stellar nurseries, cosmic wombs where new suns are forged in absolute secrecy. The darkness here is not an obstacle, it is the essential ingredient. Without it, star formation would be impossible. The process begins with a slight tug, a tiny gravitational instability within the cold gas. A pocket of material begins to condense. If this region were exposed to the intense radiation of nearby stars, the heat and pressure would blow the delicate cloud apart before gravity could gain a foothold. The dust-laden darkness acts as a perfect shield. It absorbs the disruptive energy from outside, allowing the interior to remain cold and calm. This tranquility is vital. Only in this deep freeze can gravity slowly, patiently, pull the gas and dust inward, initiating a collapse that will last hundreds of thousands of years. As the core condenses, it becomes denser and more opaque, trapping its own heat. A protostar is born, hidden within its dusty cocoon. We cannot see this with optical telescopes. The visible light these infant stars emit is immediately absorbed by the surrounding cloud. But darkness does not mean inactivity. The infrared eyes of the James Webb Space Telescope and the radio antennas of observatories like ALMA pierce this veil. They reveal a hidden universe of furious creation, showing energetic jets shooting from the protostar's poles and vast disks of material swirling around it, the raw stuff of future planets. Recent research shows that darkness works in concert with another invisible force, magnetism. Within these black clouds, magnetic fields help channel the collapsing material, guiding it onto the growing star and preventing it from spinning apart. The darkness provides the quiet, stable environment where gravity and magnetism can orchestrate the symphony of stellar birth. Every star we see in the night sky, including our own sun, was born in such a place of profound shadow. The light itself requires the dark to come into being. This reveals a beautiful symmetry. On the grandest scales, dark energy carves out the voids that define the cosmic web. On the smallest scales, the darkness within molecular clouds provides the sanctuary for gravity to build the stars that illuminate that web. The absence of light is the universe's most productive workshop. But if darkness is so fundamental to the structure and content of the cosmos, could it also be the key to its very origin, to the moment of creation itself? Our cosmic neighborhood reveals a stark environmental divide, where a galaxy's fate depends on its address within the vast architecture of the universe. We exist within the cosmic web, a magnificent lattice of dark matter filaments where most galaxies cluster together in dense cities of light. But between these brilliant filaments stretch the cosmic voids, unimaginably vast regions of near emptiness that can span hundreds of millions of light years. These are not just empty spaces between the action, they are distinct realms where galaxies experience an entirely different kind of evolution. For a galaxy living in one of these profound voids, existence is one of extreme isolation. The constant gravitational tug-of-war that shapes galaxies in crowded clusters simply does not happen here. There are no violent galactic mergers, no close encounters that strip away gas and stars, no harassment from passing neighbors. This peace and quiet allows void galaxies to evolve undisturbed, but it also comes with a cost, a profound lack of resources. In the dense filaments, galaxies regularly feast on fresh gas streaming along the cosmic web, fueling new generations of stars. A void galaxy, however, is like a solitary homesteader on a vast, empty plain. It must survive on its own original gas supply, with little opportunity for replenishment. This isolation leaves a clear imprint on their very structure. Supercomputer simulations show that without the gravitational stirring from neighbors, void galaxies often retain their irregular, misshapen forms. They fail to develop the majestic spiral arms or smooth elliptical shapes of their cluster cousins. They are also chemically primitive. The frenzied star formation and supernova explosions that enrich cluster galaxies with heavy elements happen more slowly here. Void galaxies are cosmic time capsules, preserving a more ancient, less processed state of matter. Astronomers have recognized these differences and are now using voids as natural laboratories. Projects like the Void Galaxy Survey are systematically cataloging these isolated systems, comparing them to their cluster counterparts to understand the fundamental rules of galactic growth. It is a perfect test of nature versus nurture on a cosmic scale. The darkness and emptiness of the void provide the ultimate controlled experiment, removing the variable of galactic interaction to see how a galaxy develops on its own. This research shows that cosmic emptiness is not a passive backdrop. It is an active participant in galactic design. The absence of light, the absence of neighbors, the absence of gas flows, all these voids of interaction directly determine what kind of galaxy will form. Darkness designs through both what is present and what is profoundly missing. This understanding of how emptiness shapes the largest structures forces us to look deeper, to ask if the same principles of absence might operate on the most fundamental level of reality itself. At the very core of most massive galaxies, including our own Milky Way, lies the ultimate manifestation of darkness, a supermassive black hole. These cosmic objects are so dense that not even light can escape their gravitational pull, rendering them fundamentally and perfectly dark. Their discovery was not direct, but inferred from the frantic, high-speed dance of stars at the galactic center, stars orbiting an immense, invisible mass. A profound pattern emerged from this discovery. The mass of a galaxy's central black hole is not random. It is intricately linked to the mass of the galaxy's central bulge of stars. A larger galaxy bulge means a larger black hole. This precise correlation was a stunning clue, a fingerprint left at a cosmic crime scene. It pointed to a deep, fundamental connection, a process of co-evolution where the galaxy and its dark heart grew together over billions of years. This relationship is governed by a dynamic and violent cycle of feeding and feedback. When a black hole actively pulls in matter from its surroundings, that material does not simply vanish. It forms a superheated, swirling disk of plasma just outside the event horizon, a whirlpool of doomed matter that shines with the brilliance of billions of stars. This is an active galactic nucleus, one of the most luminous phenomena in the universe. Yet this dazzling light show is just a side effect. The black hole's true power lies in the colossal energy it releases during this feast. Immense jets of particles and radiation can shoot out from its poles at nearly the speed of light, carving through the galaxy and beyond. This is the black hole's feedback mechanism. Think of it as a cosmic regulatory system. In massive galaxies, these energetic outbursts act like a global thermostat. They pump vast energy into the surrounding gas, heating it so tremendously that it cannot cool down and collapse to form new stars. The black hole, in its most active phase, can effectively quench star formation, putting a ceiling on the galaxy's growth. It is a dark heart that pumps not blood, but energy throughout the galactic body, its very darkness allowing it to control the light of future suns. We now have our first direct visual evidence of this profound darkness. The Event Horizon Telescope collaboration captured an image of the supermassive black hole at the center of Galaxy Messier 87. The now iconic picture shows a dark central shadow, the black hole's event horizon, perfectly ringed by a brilliant, lopsided halo of superheated gas. This image is not a photograph of the black hole itself, but a portrait of its gravitational grip, a perfect silhouette of absence against a backdrop of incandescent light. It is the ultimate confirmation of darkness as a tangible, structural entity. Even in death, black holes exert a dark influence. When two galaxies merge, their central black holes eventually spiral together and collide. This merger does not create a flash of light, but instead sends powerful ripples through the very fabric of spacetime itself, gravitational waves that travel across the cosmos. These waves, another form of invisible, dark energy, subtly shift the structure of everything they pass through. From the brilliant violence of their accretion to the silent tremors of their collisions, black holes demonstrate that the deepest darkness is not a destructive end. It is a creative and governing force, an engine that shapes galaxies from the shadows, determining how they live and how they evolve. The faint static hiss from a radio telescope in 1964 turned out to be the oldest song in the universe. Two astronomers, Arno Penzias and Robert Wilson, were trying to eliminate this persistent background noise from their antenna, even cleaning out pigeon droppings, but the signal remained. They had accidentally stumbled upon the cosmic microwave background radiation, the cooled remnant of the universe's first light. This is the afterglow of the Big Bang, a snapshot of the cosmos when it was just 380,000 years old. Before this moment, the universe was a hot, dense fog of plasma, opaque and blinding. Light could not travel freely, constantly scattering off free electrons. But as the universe expanded and cooled, electrons combined with protons to form the first atoms, and suddenly the fog cleared. The universe became transparent, and that first burst of light has been traveling across space ever since, stretched by expansion from visible light into microwaves. This glow is not perfectly smooth. When we map it with satellites like COBE, WMAP, and Planck, we see a mottled pattern of tiny temperature variations, anisotropies of just 1 part in 100,000. These minute fluctuations are the most important fossils in cosmology. They are imprints of the primordial darkness that existed before the light could shine. These tiny ripples represent slight differences in density across the young cosmos, but the matter that created these density variations was not the familiar atoms of stars and planets. It was the invisible scaffolding of dark matter. Because dark matter does not interact with light, It was free to begin clumping under gravity long before ordinary matter could. The dark matter distribution created a gravitational landscape of gentle hills and shallow valleys. The cosmic microwave background is a map of this dark terrain. It shows us where the dark matter was slightly denser and where it was more sparse. Think of it like a slightly lumpy cake batter. As you pour it into a pan, those tiny lumps of chocolate or fruit will determine where the final cake rises highest and where it might sink a little. The dark matter provided the lumps. The slightly denser regions, mapped by the microwave background's hotter spots, had a stronger gravitational pull. Over billions of years, they drew in more and more gas, eventually growing into the galaxies and galaxy clusters we see today. The slightly less dense regions, the cooler spots on the map, evolved into the vast cosmic voids. This is the ultimate paradox. The universe's first and most famous light is not a picture of luminous creation. It is a detailed blueprint of the primordial darkness that would structure everything. Missions like Planck have measured these fluctuations with such precision that we can read the recipe of the universe from them, determining the exact amounts of dark matter, dark energy, and ordinary matter. The light itself is a testament to the dark, a permanent record of how the faintest irregularities in the cosmic shadow became the grand architecture of existence. This ancient glow proves that darkness did not just precede the light. It designed the stage upon which the light would perform. Stephen Hawking made a discovery that shook the foundations of physics. He calculated that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they should slowly leak radiation, a faint glow now known as Hawking radiation. This process means that over unimaginable eons, a black hole can evaporate, fading away to nothing. This raised a terrifying question for physicists. According to quantum mechanics, information about what falls into a black hole, the specific arrangement of atoms that made up a star or a spaceship, can never be truly destroyed. But if the black hole itself vanishes, what happens to that information? Is it lost forever? This is the information paradox, a direct conflict between the pillars of general relativity and quantum theory. The resolution to this paradox led to one of the most radical ideas in modern science, the holographic principle. The solution proposes that information is not lost inside the black hole. Instead, it is preserved, encoded on the two-dimensional surface of the event horizon. Every particle that falls in leaves a tiny imprint on this dark surface, like a pixel on a cosmic screen. The three-dimensional interior of the black hole, with all its immense volume, is described by information painted on its two-dimensional boundary. This is not just a theory about black holes. Physicists like Leonard Susskind and Gerard T. Hooft propose that this could be a fundamental property of the entire universe. The holographic principle suggests that our entire three-dimensional reality, with all its stars, galaxies, and ourselves, might be a projection from information stored on a distant, two-dimensional surface at the edge of the cosmos. Think of an ordinary hologram like the kind on a credit card. A flat, two-dimensional surface is etched with microscopic patterns. When you shine a light on it, a stunning three-dimensional image appears floating in space. The depth and parallax are illusions, projections from the encoded data on the flat plate. The holographic principle proposes our universe operates in a similar way. The darkness of space is not an empty void. It is a vast, information-rich surface. What we perceive as the three-dimensional world is a magnificent projection from that data. This means the true laws of physics might be written in two dimensions, and our experience of a third dimension emerges from how that information is processed and perceived. The emptiness is an illusion. The darkness is dense with meaning. This transforms our understanding of absence. A black hole's event horizon, the darkest surface imaginable, becomes the ultimate cosmic hard drive. The vacuum of space itself, once thought to be nothing, is now seen as a vibrant sea of quantum information. The principle resolves Hawking's paradox by showing information is never truly inside the black hole. It is always on the surface, preserved forever in the dark. This reveals a profound truth, that the most fundamental level of reality might not be made of particles or forces, but of bits of information. Darkness is not the absence of something. It is a different form of presence, an informational substrate from which all light and matter are forged. The void is not empty, it is full. These cosmic mysteries are not confined to the heavens alone. Physicists are now recreating the universe's deepest darkness right here on Earth, inside remarkable laboratory experiments. They build analog universes to watch these abstract principles in action. One of the most powerful tools is the Bose-Einstein condensate, a state of matter where atoms are cooled to near absolute zero. At this extreme cold, atoms lose their individuality and behave as a single quantum wave. Researchers can manipulate this superfluid cloud, making it expand or contract in a way that perfectly mimics the expansion of the cosmos itself. Within this controlled environment, they can directly observe the effects of this simulated expansion on quantum fields. Just as the stretching of space-time in the early universe is thought to have amplified quantum fluctuations into the seeds of galaxies, the stretching of the condensate creates ripples and particles from the quantum vacuum. Scientists have literally watched spontaneous particle creation occur in these tabletop universes, providing stunning experimental support for the quantum processes that likely shaped our entire cosmos. Another line of investigation recreates the intense gravity of black holes. Using flowing water, laser pulses, or even sound waves, physicists engineer analogs of an event horizon. In one famous experiment, a team created a waterfall so steep that the water flowing over it moved faster than the waves on its surface. This creates a point of no return for ripples, exactly like a black hole's event horizon for light. In these analog black holes, researchers have detected the telltale signs of Hawking radiation, the spontaneous emission of particles predicted to occur at real event horizons. The analog system produces pairs of waves, one falling into the waterfall and one escaping, precisely mirroring the quantum pair production at a true black hole. It is a shadow of the real phenomenon, but a powerful confirmation that the physics of darkness holds firm. Think of these experiments as cosmic wind tunnels. Aerospace engineers do not need to fly a plane at Mach 5 to understand its aerodynamics. They test a scaled model in a controlled chamber. In the same way, physicists do not need to travel to a black hole to test Hawking's ideas. They build a scaled analog and observe the principles at work. These laboratories are testing grounds for the most fundamental forces of cosmic design. They allow us to probe the nature of vacuum energy, to watch quantum fluctuations spark into existence, and to verify that the strange physics of absence is not just mathematical speculation, but a robust feature of reality. This experimental work bridges the vast gap between the abstract equations of general relativity and the tangible, observable universe. It demonstrates that the creative power of darkness is a phenomenon we can not only conceive of but actually study, measure, and begin to truly understand. This invisible sea of quantum foam is not just a cosmic curiosity. It exerts a tangible, physical push. We can measure its force right here on Earth through a remarkable phenomenon called the Casimir Effect. Picture two incredibly smooth, uncharged metal plates placed almost impossibly close together in a perfect vacuum, mere nanometers apart. In the vast emptiness outside the plates, every wavelength of virtual particle can flicker into existence. But in the narrow gap between them, only certain wavelengths can fit. This creates a pressure imbalance, with more virtual particles pushing on the plates from the outside than from the inside. The result, the plates are pulled together by the nothingness itself. It is a direct, laboratory proof that the vacuum is alive with fluctuation, and that this darkness exerts a real force. This understanding is moving from theoretical physics into engineering. In the world of nanotechnology and microelectromechanical systems, or MEMS, these tiny devices are so small that vacuum fluctuations can cause their components to stick together, a phenomenon called stiction that engineers once saw as a nuisance. Now, by embracing the Casimir force, they are beginning to design around it, even harnessing it to create frictionless bearings and ultrasensitive switches where the vacuum itself becomes a component of the machine. This is darkness engineering, designing with the hidden energy of empty space. The logical next question is breathtaking. Could we actually extract useful energy from this quantum sea? Theoretically, yes, but the challenges are monumental. The vacuum energy is everywhere at once, like an infinite ocean, but tapping it is like trying to harness the energy of the sea by bobbing on a raft. You are already a part of the system. Thermodynamics places strict limits, meaning any device that tries would likely consume more energy than it produces. Yet, this has not stopped serious theoretical work. Some proposals involve ultra-fast optical switches or superconducting circuits that might momentarily borrow energy from the vacuum, creating a burst of power before the debt is repaid. We already see glimpses of this potential in existing technology. Quantum levitation, where superconductors lock in place over magnets, relies on the quantum trapping of magnetic fields, a cousin to the same vacuum phenomena. In advanced optics, laser systems are now so precise that their operation is subtly influenced by the vacuum field, a factor that must be accounted for in their design. The most speculative frontier involves concepts like the quantum vacuum thruster, a hypothetical engine that would attempt to push against the virtual particles of the vacuum to generate thrust without expelling propellant. While such ideas are deeply controversial and face immense scientific skepticism, they drive research that further illuminates the strange physics of nothingness. The most immediate and profound applications are not in star drives, but in the bedrock of modern technology. Our entire understanding of quantum vacuum fluctuations is crucial for developing quantum computers. The fragile state of a qubit, the basic unit of quantum information, can be easily disrupted by the faint whispers of the vacuum environment. To build a reliable quantum computer, we must learn to shield it from this dark noise, or even better, to manipulate the vacuum itself to protect the qubit's delicate state. This research also leads to unimaginably precise measurement devices. Atomic clocks, which use the vibration of atoms to keep time, are so accurate they would lose less than a second over the entire age of the universe. Their precision is constantly being improved by accounting for minute interactions with the quantum vacuum. This journey from cosmic wonder to practical tool reveals a beautiful truth. Our investigation into the deepest darkness of the universe, driven by pure curiosity about black holes and the void, consistently circles back to revolutionize our world. The same principles that govern the birth of galaxies are now guiding the design of nanotechnology and the pursuit of unhackable quantum communication. It demonstrates that fundamental research into the nature of reality is not an abstract luxury. It is the ultimate source of technological innovation. By staring into the void and asking what it is, we are ultimately given new ways to see, to measure, and to create. The hollow center of a clay pot is what grants it its purpose. This ancient insight from Taoist philosophy points toward a universal principle, that usefulness arises from what is not there. The space within a room, the emptiness between the walls, is what makes it a place we can inhabit. For millennia, Eastern traditions like Taoism and Buddhism have contemplated the creative power of Wu, or non-being. They saw the void not as a barren absence, but as the fertile ground from which all things spring, the silent source that gives rise to the 10,000 things of the manifest world. This perspective does not see darkness and light, or emptiness and form, as enemies. They are complementary partners in a continuous dance of creation, each giving meaning and function to the other. This philosophical embrace of the void stands in stark contrast to a deep-seated thread in Western thought. Here, nothingness was often a source of dread. Existentialist philosophers like Jean-Paul Sartre famously declared that man is a passion in vain, a being haunted by the nothingness from which he emerged and to which he will return. For Sartre, this absence of inherent meaning was the source of anguish, but also of radical freedom because it forced us to create our own purpose. His predecessor, Martin Heidegger, delved even deeper into the nature of being and its relationship to nothingness. He argued that we can only truly understand what it means to be by confronting the abyss of not being. It is the silent backdrop against which existence is thrown into sharp relief. These philosophical wrestlings with the void now find a startling echo in the language of modern physics. The quantum vacuum is not the sterile, empty nothingness the existentialists feared. It is a plenum, a state of infinite potential buzzing with virtual particles and energy fluctuations. Science has not eliminated nothingness, it has transformed it from a terrifying absence into a pregnant fullness. The void is not empty, it is vital. This convergence of thought is not a coincidence. It suggests that both intuition and investigation are pointing toward the same profound truth about the nature of reality. We can see this principle at work in art and music. The rests between notes are not merely pauses in the melody, they are essential to its rhythm and emotional impact. The silence gives the sound its shape and meaning. In the same way, the dark matter scaffolding and the cosmic voids are the silent rests in the symphony of the cosmos, the necessary absences that give structure and form to the luminous notes of the galaxies. Contemporary philosophers of science like David Albert and Carlo Rovelli argue that physics has fundamentally redefined nothingness. It is no longer the absolute zero of existence, but a field of immense potentiality, a something that behaves in ways we are only beginning to comprehend. This shifts our entire cosmological framework. The universe may not have erupted into being from a state of true nothingness in the philosophical sense, but from a pre-existing quantum state rich with informational potential, a dark and vibrant sea of possibility. This unified view dissolves the old opposition between absence and presence. They are not opposites but partners. Darkness does not oppose light, it collaborates with it. Emptiness does not contradict fullness, it makes it possible. The philosophical void and the quantum vacuum are not two different concepts, but two different languages describing the same creative source. The hollow at the center of everything is not a lack to be filled, but the very reason anything can exist at all. The steady-state model offered a serene vision of an eternal universe. Its proponents, including Fred Hoyle, argued that the cosmos had no beginning and no end. To explain the observed expansion, they proposed a continuous and subtle creation of new matter in the voids between galaxies, just enough to maintain a constant density over time. In this view, empty space was not truly empty. It was a creative medium, perpetually giving birth to new atoms to preserve a perfect, unchanging cosmos. This elegant idea was ultimately undone by evidence, most decisively by the discovery of the cosmic microwave background. That faint hiss was the death knell for the steady state, as it was the clear, cooled remnant of a hot, dense beginning, a singular event we now call the Big Bang. The universe was not in a steady state, it was evolving, and its history was written in the fading glow of its birth. This victory for the Big Bang model came with its own set of profound puzzles. Why was the universe so incredibly uniform in all directions? How did such vast, smooth structures emerge? The theory needed a new mechanism, a cosmic catalyst. The answer arrived with a breathtaking proposal, inflationary cosmology. This theory posits that a fraction of a second after the Big Bang, The universe underwent a fantastically brief period of hyper-accelerated expansion, inflating by an unimaginable factor in less time than it takes light to cross a proton. This explosive growth stretched the fabric of spacetime itself, ironing out any primordial wrinkles and leaving the smooth, flat universe we observe. But inflation did something even more remarkable. It took the faintest quantum whispers, the microscopic fluctuations in the energy fields that fill the vacuum, and stretched them to astronomical sizes. Those tiny quantum ripples became the gravitational seeds for everything: the future galaxies, clusters, and vast voids. The largest structures in existence were born from the smallest possible vibrations in the dark. This inflationary framework did not just explain the universe's structure. It made precise predictions about its composition. The physics that drove inflation also dictated the specific amounts of dark matter and dark energy required for the universe to have the geometry we observe. The model demands a universe that is flat, and for that to be true, the total density of all energy and matter must equal a critical value. Ordinary atoms, the stuff of stars and planets, account for less than 5% of that total. The rest must be dark. Modern precision cosmology has measured this recipe through multiple, independent lines of evidence: the patterns in the cosmic microwave background, the large-scale distribution of galaxies, the gravitational lensing of light by invisible mass, and the accelerating expansion traced by distant supernovae. They all tell the same story. They all converge on a cosmos made of about 27% dark matter and 68% dark energy. The darkness is not a minor component. It is the overwhelming majority of reality, and its precise quantities are a direct prediction of our best theory of cosmic origins. This historical journey, from the rejected continuous creation of the steady state to the quantum-powered inflation of the Big Bang, charts a clear course. Our scientific understanding has progressively shifted from seeing emptiness as a passive backdrop to recognizing it as the active, dynamic source of cosmic design. The void is not incidental, it is fundamental. This hard-won consensus, however, is not the final word. The frontier of cosmology is alive with physicists proposing even more radical alternatives, theories that challenge our very definitions of darkness and reality. What if our fundamental understanding of gravity is simply incomplete? This is the provocative question at the heart of one of cosmology's most intriguing alternatives to dark matter, a theory known as modified Newtonian dynamics, or MN. Proposed by physicist Mordechai Milgram in the early 1980s, MN suggests that we do not need vast halos of invisible matter to explain galaxy rotation curves. Instead, the force of gravity itself might behave differently under certain conditions. Newton's laws work perfectly within our solar system and in most laboratory tests, but Milgram proposed a subtle change, a new constant of nature. He suggested that at extremely low accelerations, far weaker than anything we experience on Earth, gravity becomes stronger than Newton or Einstein predicted. This tiny adjustment to the math makes the outer stars in a galaxy orbit faster without any need for dark matter's gravitational pull. It is like realizing the rules of fluid dynamics change for a trickle of water compared to a rushing river. In many individual galaxies, MN works astonishingly well, often providing a more precise fit to the observed rotation than the standard dark matter model does. It is an elegant solution that removes the need for an entire invisible component of the universe, but elegance often meets complexity when faced with all the evidence. While MN excels with single galaxies, it begins to falter on larger scales. When scientists apply its equations to the dynamics of entire galaxy clusters, the math falls short. There still appears to be a significant amount of missing mass holding these immense structures together, mass that MN cannot account for. Furthermore, The theory in its original form could not explain the precise pattern of the cosmic microwave background or the detailed gravitational lensing we observe from massive clusters. To address these shortcomings, physicists have developed more sophisticated, relativistic versions of MND. Theories like tensor vector, scalar gravity, or TVS attempt to weave modified gravity into a framework compatible with Einstein's general relativity. More recently, ideas like emergent gravity have proposed that gravity is not a fundamental force at all, but a side effect of the quantum information structure of spacetime, an entropy-driven phenomenon that naturally produces effects which look like dark matter. On the dark energy front, similar rethinking is underway. Perhaps the accelerating expansion is not caused by a cosmological constant, a fixed energy inherent to space itself. Maybe the fundamental constants of nature, like the strength of gravity or the mass of an electron, are slowly changing over cosmic time. Or perhaps our universe is just one membrane floating in a higher dimensional space, and the push from these other dimensions manifests as dark energy. The choice between these models is like trying to figure out why a room is cold. You could assume there is a hidden, unseen heater that is broken, which is the dark matter approach, postulating an invisible component to explain the effect. Or you could re-examine the walls and windows, questioning if your understanding of insulation itself is flawed, which is the modified gravity approach, changing the rules of the game. Both explanations can account for the chilly temperature, but they imply radically different things about the building's construction. How do we decide which is correct? The scientific process is now running these experiments. Astronomers are studying the motions of wide binary stars, pairs of stars orbiting each other at vast distances where gravitational accelerations are incredibly faint. This is the perfect regime to test MND predictions against those of Newtonian gravity with dark matter. Other projects are looking for subtle signatures in the cosmic web, or the echoes of gravitational waves that could reveal if Einstein's theory needs a tweak. This active investigation is not a sign of weakness in cosmology. It is its greatest strength. The healthy competition between dark matter and modified gravity theories ensures that scientists remain critical, constantly testing assumptions and seeking the most complete explanation. It prevents dogmatism and drives innovation, pushing our tools and telescopes to ever greater precision. The true nature of cosmic darkness remains an open question, and the final answer may be something far stranger than anything we have yet conceived. The Euclid Space Telescope, launched in 2023, is now charting a map of the invisible. Its mission is to observe billions of galaxies across 10 billion years of cosmic history, not for their light, but for their dark distortions. As the light from these distant galaxies travels toward us, it is subtly bent by the gravitational pull of unseen dark matter clumps along the way, a phenomenon called weak gravitational lensing. By meticulously measuring these tiny warps and twists in the shapes of galaxies, Euclid will trace the hidden distribution of dark matter with unparalleled detail, revealing the cosmic web in stark relief. Simultaneously, it will measure the rate of the universe's expansion over time, probing the nature of dark energy itself. This is not a single snapshot, but a cosmic film, allowing us to watch how dark energy has shaped the universe across eons. Following closely behind is NAS, a Nancy Grace Roman Space Telescope, set for launch in the mid-2020s. With a field of view 100 times larger than the Hubble Space Telescope's infrared camera, Roman will conduct vast, deep surveys at breathtaking resolution. It will discover thousands of new exoplanets, but its primary mission is to stare into the abyss, capturing the signatures of dark energy's influence and hunting for primordial black holes that could be a component of dark matter. It will essentially take a cosmic census of the darkness, counting the invisible through its profound effects on the visible. On the ground in Chile, the Vera Sea. Rubin Observatory is preparing for its legacy survey of space and time. This project will not simply look at the sky, it will watch it, night after night for a decade, creating an unprecedented time-lapse movie of the cosmos. Its enormous mirror and massive camera will detect the most subtle changes, spotting fleeting events and measuring the gentle shearing of galaxy shapes caused by dark matter's gravitational lensing on a colossal scale. This relentless observation will allow scientists to construct a dynamic, three-dimensional map of the dark matter scaffolding as it evolves. The search also descends deep underground. In abandoned gold mines and beneath mountains, ultra-sensitive experiments like LUX Zeppelin and Xeno NNT wait in profound silence and cold. Sheltered from cosmic rays, their tanks of ultra-pure liquid xenon are designed to feel the faintest whisper of a passing dark matter particle, a potential bump from a WIMP, or weakly interacting massive particle. A single, rare interaction could be the first direct touch of the dark universe. Meanwhile, at high altitudes in the Chilean Andes and at the South Pole, a new generation of cosmic microwave background experiments is coming online. The Simons Observatory and the future CMBS-4 project will use arrays of ultrasensitive microwave detectors to map the faint afterglow of the Big Bang with microscopic precision. They are reading the original blueprint of darkness, looking for the faint imprint of primordial gravitational waves or clues about the mass of neutrinos, which could shift our understanding of the dark matter recipe. Think of this global effort as humanity developing a new form of vision. For centuries, we had only optical eyes. Then we learned to see in radio waves, in X-rays, in infrared. Now, we are collectively forging the ability to see through gravity itself, to perceive the hidden masses and energies that weave the fabric of space. Each mission provides a different filter, a different wavelength of insight. Alone, they see a part of the truth. Together, they will converge into a single, multi-messenger picture of the dark universe, a holistic view where the gap between the quantum vacuum and the cosmic web might finally close. The data from these projects will flood in over the next decade, offering the very real potential to resolve the enduring mysteries of dark matter and dark energy. We may confirm their natures, or we may be forced to rewrite the textbooks entirely, discovering that the darkness is something even more bizarre and wonderful than we currently suppose. This is not the end of the story, but the beginning of its most exciting chapter. Our textbooks often paint a universe of stars and galaxies, a brilliant spectacle against a passive, black backdrop. This light-centric narrative, while beautiful, is a relic of an older understanding, one that treats darkness as an empty stage rather than the lead architect. To teach astronomy this way is to show someone a tree and call it a forest, completely missing the ecosystem that gives it life. We must move beyond this limited view and begin presenting the cosmos as it truly is, a realm where the unseen majority dictates the fate of the luminous minority. This shift means introducing concepts like dark matter and dark energy not as advanced footnotes, but as fundamental characters in the story of cosmic evolution from the very beginning. Imagine a student learning about gravity not just from the fall of an apple, but from a simple, stretched spandex sheet. Placing a heavy weight in the center creates a well, a model of a star's gravity. But then, sprinkling fine sand around the weight to represent dark matter shows how this invisible halo creates a deeper, broader gravitational landscape that guides the orbits of marbles, the planets. This tangible model makes an abstract force visible, or consider a ripple tank in a physics class. The waves are the light, the matter we see, but the medium through which the waves travel, the water itself, is the quantum vacuum, the vibrant, energetic darkness that makes the propagation of those waves possible. We can see the waves, but we must understand it is the properties of the hidden medium that defines their behavior. This pedagogical evolution has a powerful parallel in biology. For generations, Photosynthesis was taught as a process driven purely by light absorption. Today, we know the Calvin cycle, the so-called dark reactions, are equally vital, using the energy captured from light to actually build the sugars that fuel life. The light provides the spark, but the foundational construction happens in the biochemical shadows. Our educational institutions must embrace this complete picture. Planetarium shows can project not just the pinpricks of starlight, but the inferred web of dark matter filaments connecting them, creating a glowing neural network of the cosmos. Museum exhibits can feature interactive displays where visitors manipulate the density of dark energy in a simulation and watch the fate of a virtual universe unfold before them. Digital resources like science websites already offer visualizations that make the invisible visible, tools that should be front and center in every classroom. This approach does more than just update facts. It teaches the very nature of science. It shows students that our understanding is not static, that discovery is an ongoing process of questioning what we cannot see. It demonstrates that the biggest mysteries are not flaws in our knowledge, but invitations to explore further. By framing darkness as creative and fundamental, we give students a more accurate, more dynamic, and ultimately more exciting vision of the universe, one where the greatest stories are still hidden in the shadows, waiting to be told. This revised perspective on cosmic education naturally invites us to ask how these profound scientific ideas are being reflected back to us in the stories we tell about ourselves. Ancient Egyptians envisioned the endless, dark waters of Nun, a formless void that existed before time, containing within its silent depths the potential for all gods and all life. This intuition that creation blossoms from a dark womb echoes across human history. The ancient Greeks began their cosmology with chaos, a yawning gap of nothingness, while the Hebrew book of Genesis opens upon the face of the deep, a tehom of watery darkness from which God summons light and order. In Aboriginal Dreamtime stories, the ancestral spirits emerge from an eternal, featureless night to sing the world into existence. Across these traditions, darkness is never a mere emptiness waiting to be filled. It is the original state, the fertile ground of all possibility, the creative source itself. This primordial darkness was not feared, but revered as the mother of everything. Long before telescopes or particle accelerators, the human spirit sensed a profound truth about the cosmos, that absence holds a unique and potent creative power. This intuition did not remain confined to sacred texts. It poured into the arts, becoming a fundamental tool of expression. The Dutch master Rembrandt harnessed darkness not as a void, but as a substance. His technique of chiaroscuro, the violent interplay of light and shadow, used deep, velvety blacks to sculpt his subjects from the gloom. In his paintings, the darkness is active. It cradles faces, reveals emotion, and directs the viewer's gaze, proving that what is hidden can be more powerful than what is shown. Centuries later, J.M.W. Turner would push this further, dissolving solid forms into luminous obscurity. His seascapes and storms are vortices of energy where light seems to be born from the chaotic, dark swirls of paint, mirroring the cosmic emergence of stars from nebulous dust. Literature, too, has consistently returned to the generative power of the dark. Dante Alighieri begins his Divine Comedy lost in a dark wood, a place of terror and confusion that nevertheless becomes the necessary starting point for his transformative journey through the cosmos. This narrative archetype of the dark night of the soul that precedes enlightenment is a human universal. In our modern era, science fiction authors explore the cosmic void not just as a setting for travel, but as a character. The overwhelming, silent blackness between stars in stories by Arthur C. Clarke or Alastair Reynolds becomes a catalyst for awe, terror, and ultimately, a deeper understanding of our fragile place in the universe. Today's artists are directly engaging with the scientific mysteries of darkness, translating data into experience. Sculptors create installations based on the inferred distribution of dark matter, giving tangible form to the invisible scaffolding of the cosmos. Digital artists use simulations of quantum vacuum fluctuations to generate swirling, hypnotic visualizations of the seething energy in empty space. These works are a modern mythology, using the tools of our time to explore the same ancient wonder at the creative potential of the unseen. This enduring cultural thread, from the oldest myths to the newest media installations, reveals a deep and persistent human wisdom. It suggests that our scientific discovery of dark matter's formative grip and the quantum vacuum's vibrant energy is not a radical break from past thought, but a validation of a timeless intuition. We have always felt in our stories and our art that the darkness is not a blank. It is a participant. It is the canvas, the raw material, and the quiet architect, working in the shadows to bring the light into being. We flood our nights with artificial light and our minds with endless streams of information, building a fortress against the quiet and the dark. This constant stimulation seems like progress, but we may be walling ourselves off from a fundamental source of creativity, one that the cosmos has relied upon since the beginning. Just as the profound darkness of a molecular cloud provides the quiet necessary for gravity to build a star, our own minds require periods of uninterrupted stillness to form new connections and insights. Psychological studies consistently show that moments of boredom, daydreaming, and rest are not wasted time. They are the incubators for our most original ideas. It is in the mental void, when we are not actively focused on a task, that our brain's default mode network activates, quietly solving problems and weaving together disparate thoughts into novel concepts. This is the human equivalent of the quantum vacuum, a seemingly empty mental space that is actually buzzing with potential, waiting for the right conditions to manifest a spark of inspiration. Consider the structure of a beautiful piece of music. The notes themselves carry the melody, but it is the rests, the deliberate silences between them, that give the composition its rhythm, emotion, and power. Without those pauses, the sound would be nothing but an overwhelming noise. In the same way, the silence between our words is what makes communication possible, providing the necessary space for meaning to land and be understood. This principle is central to many meditation traditions, which practice resting in empty awareness, the clear and open ground of consciousness from which all thoughts emerge and to which they return. The goal is not to stop thinking, but to recognize that our essential being is like the cosmic void, not a blank emptiness, but a spacious and creative presence that holds all experience. We can integrate this understanding into our daily lives in simple, practical ways. A digital detox for an hour each evening creates a pocket of mental darkness, allowing your thoughts to settle and rearrange. A silent walk, without headphones or a podcast, invites the subconscious mind to work on challenges you are facing. Even just sitting in a dimly lit room for a few minutes can become a sanctuary, a personal cosmic void where new ideas can condense from the quiet. Embracing these moments is not about rejecting light and activity, but about honoring the essential creative partnership between presence and absence, between the particle and the void. The same cosmic darkness that sculpts galaxies and births stars also operates within the architecture of our own minds, offering a wellspring of clarity and creativity when we allow ourselves to simply be in the dark. The crushing blackness of the deep ocean is the closest we can come to an alien world without leaving Earth. In the Hadal Zone, at depths exceeding 6,000 meters, sunlight is a forgotten myth. The pressure is immense, and the temperature hovers just above freezing. This is an environment of profound and permanent darkness, a place that seems utterly hostile to life. Yet it teems with it. The discovery of thriving ecosystems around deep-sea hydrothermal vents in the 1970s was a revolution in biology. Here, in the absolute dark, life does not depend on the sun. It runs on an entirely different engine, chemosynthesis. Bacteria harness the chemical energy from minerals spewing from the Earth's crust, converting hydrogen sulfide and other compounds into organic matter. These bacteria form the base of a bizarre and magnificent food web, supporting towering tube worms, ghostly white crabs, and strange, eyeless fish. This is a world built not on light, but on geology, proving that life can find a way in the deepest dark, independent of the star that powers our surface existence. Similarly, the polar night presents another extreme of terrestrial darkness. For months on end, the Arctic and Antarctic are plunged into unending twilight or total blackness. We once assumed this period was a biological shutdown, a hibernation for the frozen north. But advanced research has revealed a different story. Life does not simply pause. It adapts. Zooplankton undertake massive daily vertical migrations, rising from the depths under the cover of darkness to feed. Fish and other marine life exhibit reduced activity, but their metabolism is finely tuned to conserve energy while remaining ready to seize opportunities. Some creatures develop enhanced sensory capabilities, relying on touch and sound to navigate and hunt in the void. The darkness is not a barrier, but a different set of rules, forcing evolution to innovate in remarkable ways. One of the most stunning adaptations to these dark realms is bioluminescence. In the deep sea, where no sunlight penetrates, countless organisms create their own light. The anglerfish dangles a luminous lure to attract prey. Jellyfish pulse with eerie blue-green light. Even the water itself can sparkle with 1,000,000 points of light from microscopic dinoflagellates when disturbed. This is not light borrowed from the sun, it is light generated from within, a biological rebellion against the void. These creatures use light as a tool for hunting, for camouflage, for communication, and for mating. They have taken control of illumination itself, turning the absolute darkness into a canvas for their own creations. These earthly examples are powerful analogies for the cosmic scale. The chemosynthetic ecosystems of the deep ocean vents show us that energy and creation can come from unexpected, non-solar sources, much like the quantum vacuum energy that might power processes in the emptiness of space. The persistent biological activity during the polar night demonstrates that darkness is not synonymous with inactivity. Just as the apparent void between stars is seething with quantum potential and the gravitational influence of dark matter. And the phenomenon of bioluminescence, where life generates its own light in the abyss, mirrors the way stars and galaxies ignite within the dark cosmic web, creating their own brilliant islands in the vast blackness. By studying how life not only survives but thrives in the darkest places on our planet, we gain a deeper appreciation for how the universe itself might be teeming with activity and innovation within its greatest voids. This understanding forces us to look up at the night sky not as a barren expanse, but as a deep ocean of possibility, waiting for us to learn how to see in the dark. Gravitational lensing is astronomy's most elegant magic trick, turning empty space into a cosmic magnifying glass. We cannot see the immense halos of dark matter surrounding galaxy clusters, but we can watch them warp the fabric of spacetime itself. When light from a distant galaxy travels toward us, its path is bent by the gravitational pull of this invisible mass, distorting the galaxy's image into faint, smeared arcs or even multiple mirage-like copies. This effect, predicted by Einstein, is our most direct window onto the dark universe, allowing us to literally map the unseen by tracing its profound effect on the light we can capture. It is like deducing the shape of a mountain pass by watching how the wind sculpts the snowdrifts. We see the sculpture, and from it we infer the sculptor. Within the crowded hearts of galaxy clusters, another telltale sign of darkness emerges from the chaos of motion. By measuring the velocity dispersion, the spread of speeds at which thousands of individual stars and galaxies are hurtling about, astronomers can weigh the entire cluster. The results are always the same. The visible matter, all the brilliant stars and glowing gas, accounts for only a fraction of the gravitational glue needed to hold such a massive structure together. The stars are moving far too quickly to be bound by the gravity of what we see, like children on a merry-go-round spinning so fast it should fly apart. Yet it remains intact, held by hands we cannot see. This celestial fingerprint proves that an immense quantity of dark matter must be present, its gravity alone providing the necessary pull to keep the cluster from flying apart. On the largest scales, the story is written in the positions of galaxies themselves. Meticulous surveys like the Sloan Digital Sky Survey have mapped the three-dimensional locations of millions of galaxies, revealing the universe's grand architecture. This cosmic web is a vast, sponge-like structure of dense filaments and immense empty voids. The distribution is not random. The galaxies trace out the underlying gravitational scaffolding of dark matter. But the voids are not merely empty space. Their sizes and shapes are governed by the relentless push of dark energy, which stretches these empty regions ever larger over cosmic time. By studying the patterns of what is present, we are actually reading the signature of what is profoundly absent, learning how dark energy's repulsive force sculpts the largest structures in existence. The quest to see the unseen now employs a new generation of tools that listen to the darkness. Radio telescopes tuned to the 21-centimeter wavelength can detect the faint emission from neutral hydrogen gas, the raw material of stars, that drifts in the dark regions between galaxies. This allows us to trace the flows of invisible matter. Meanwhile, incredibly sensitive instruments at the South Pole and in space study the polarization, the specific orientation, of the cosmic microwave background. Within this subtle pattern may lie the faint imprint of primordial gravitational waves, ripples in spacetime from the universe's first violent moments of inflation, a whisper from the dawn of time encoded in the oldest light. This entire endeavor is a testament to scientific ingenuity, a discipline that transforms the fundamental obstacle of darkness into its richest source of information. We are like detectives at a crime scene where the culprit has vanished without a trace. We cannot see the criminal, but we can study the bent lock, the displaced rug, the faint footprint, and from these clues we build a complete picture of the unseen actor. By reading the subtle language of effects, we are slowly learning to speak the mother tongue of the cosmos, a language written not in light, but in the graceful, invisible curves of gravity and the silent, expansive push of nothingness itself. A chemical reaction cannot begin without first overcoming a barrier known as activation energy. This is the initial investment of power required to break old bonds before new ones can form. For a fleeting moment, the reacting molecules exist in a transitional state of higher energy, a precarious and invisible threshold between what was and what will be. This necessary dark space of potential is what makes transformation possible, ensuring that not every collision results in a reckless explosion, but that change occurs with deliberate, structured intention. Ecologists observe a similar principle at work in nature's intricate webs. The intermediate disturbance hypothesis proposes that ecosystems achieve their greatest richness and diversity not in states of perfect calm or utter chaos, but under conditions of moderate, periodic stress. A forest fire, while destructive, clears the canopy and allows sunlight to reach the forest floor, triggering a burst of new growth and opportunity for dormant species. This perturbation is the ecological equivalent of a cosmic void, a creative darkness that carves out space for innovation and complexity to flourish by disrupting a stable, and often stagnant, status quo. This dance between structure and emptiness is engineered directly into the materials that shape our world. In metallurgy, the strategic introduction of tiny voids or dislocations within a crystal lattice can dramatically increase a metal's strength and malleability. The carefully designed emptiness in aerogels, the lightest solids known, gives them incredible insulating properties. Modern architects use this same principle, creating structures that are not solid blocks, but precisely calculated lattices of material and space, where the absence of mass is what grants them both strength and grace. Even our most abstract systems of thought are built upon the formalization of nothing. The invention of zero was a revolutionary leap in mathematics, transforming cumbersome Roman numerals into the elegant logic of place-value notation that powers all modern computation. The concept of the empty set, a container holding nothing, became a foundational cornerstone for set theory and modern logic. These tools for describing absence are what allow us to model everything from the orbits of planets to the flow of information across a network. Perhaps the most personal expression of this principle operates within our own minds. Neuroscience has revealed that when our brain is not focused on an external task, a rich internal network activates. This default mode is not a state of mental idleness, but a period of intense activity where memories are consolidated, past experiences are integrated, and the seeds of creativity are sown. Our most brilliant insights often emerge from this mental darkness, from the cognitive space between our deliberate thoughts. From the energy barrier in a test tube to the silent workings of our own consciousness, a universal pattern emerges. Complex systems, whether they are made of molecules, stars, or ideas, do not organize through presence alone. They require the creative tension of absence, the structuring power of the void, the dark potential that exists between stable states. This interplay is the silent engine of transformation across every scale of reality, a fundamental rhythm of construction and deconstruction that writes the story of the universe itself. Quantum mechanics was once dismissed as an abstract intellectual game. Today, it powers the entire modern world. The transistors in every computer and smartphone rely on the quantum behavior of electrons. The lasers in our fiber optic networks and medical devices are quantum tools. Magnetic resonance imaging, or MRI, machines use quantum principles to peer inside the human body without a single cut. These technologies, representing trillions of dollars in global economic activity, all sprang from research into the fundamental, seemingly impractical nature of reality. The journey to understand the cosmos follows the same path. The quest to capture faint starlight led directly to the charge-coupled device, or CCD, the sensor that revolutionized digital photography and now sits in every phone camera. The sophisticated algorithms developed to clean up noisy images from deep space telescopes are now used by doctors to sharpen MRI scans and detect tumors with incredible precision. Even our daily navigation depends on cosmic physics. The global positioning system in your car or phone must account for Einstein's theory of general relativity. The satellite's atomic clocks tick at a slightly different rate than clocks on Earth due to gravity's warping of time. Without correcting for this esoteric effect, GPS coordinates would drift by several miles each day, rendering the system useless within minutes. This is not a coincidence, it is a pattern. Pushing the boundaries of fundamental knowledge, even about something as abstract as cosmic darkness, consistently unlocks unforeseen practical benefits. The economic argument extends beyond tangible inventions. This research trains a world-class workforce. The physicists and engineers who design ultra-sensitive detectors to hunt for dark matter or build telescopes to map the void develop unparalleled problem-solving skills. They master advanced computing, material science, and data analysis. These experts then flow into the broader economy, bringing their innovation to sectors like finance, computing, and engineering. They become the innovators who drive progress across countless industries. Of course, such ambitious research requires significant investment. Critics rightly ask if these funds could be better spent addressing immediate problems on Earth. Yet history shows that fundamental science offers one of the highest returns on investment of any public funding. It seeds the technological forests from which future industries will grow. We did not know we needed the internet until it was invented at CERN to help physicists share data. We could not have predicted that studying the spin of atomic nuclei would lead to life-saving medical diagnostics. The very act of exploring the unknown, of trying to answer profound questions about dark matter and dark energy, forces us to develop new tools, new materials, and new ways of thinking that inevitably spill over into society, creating wealth, health, and security. Investing in the darkness is not a diversion from practical concerns. It is one of the most practical long-term investments we can make. This tangible value, however, leads us to a deeper, more ethical consideration. This profound connection to the cosmic dark is a birthright we are rapidly surrendering. For 80% of humanity, the Milky Way is now invisible, washed out by the relentless glow of artificial light. We have engineered a perpetual twilight that severs our direct visual link to the universe, disconnecting us from the very context of our existence. This light pollution acts like a veil, obscuring the grand architecture of dark matter and the vast voids that our journey has explored. But the consequences are far more than philosophical. Entire ecosystems depend on the natural rhythm of darkness, and our interference has devastating effects. Sea turtle hatchlings instinctively navigate toward the moonlit ocean, but now they are drawn inland by streetlights, leading to certain death. Migratory birds, who use the stars to guide their epic journeys, become disoriented by urban glare, circling until they drop from exhaustion. The intricate cycles of reproduction, pollination, and predation, all finely tuned to the day-night cycle, are thrown into chaos by our endless artificial day. It is akin to noise pollution drowning out the subtle, essential frequencies that animals use to communicate and survive. We are flooding the world with a visual cacophony that silences the natural world. In response, a growing dark sky movement is fighting to preserve the night. International dark sky places are designated sanctuaries where artificial light is carefully controlled, protecting the clarity of the heavens for both powerful telescopes and the naked human eye. These efforts are not just for astronomy, they are for ecology and our own human spirit. To stand in true darkness and look up is to experience a profound perspective shift, a humbling reminder that we are part of something vastly larger than ourselves. Losing that experience is an ethical failure, a theft of wonder from future generations. It represents a closing of the cosmic eye, a willful ignorance of the dark, creative universe we are only beginning to understand. Preserving natural darkness is not a rejection of progress, but an affirmation of our need to remain connected to the reality of the cosmos, both its brilliant light and its essential, shaping dark. The quantum vacuum is not a silent void but a chorus of probabilities, a sea of information waiting to be read. Every fluctuation is a bit of data, a momentary yes or no in the language of existence, and the universe is a vast computer processing these choices. This informational view unites every thread of our journey. The faint density ripples in the early universe, imprinted on the cosmic microwave background, were the first data points, the initial conditions written into the fabric of reality. Dark matter is the hardware that stored this information, its gravitational pull organizing that raw data into the three-dimensional structure of the cosmic web. And dark energy is the algorithm now running, its expansive push determining how that structure will evolve and what forms will ultimately survive. This perspective transforms our understanding of emptiness. A void is not a blank space. It is a domain of specific information, a region where the data dictates a low density of matter. The holographic principle takes this idea to its ultimate conclusion, suggesting that all the information describing our three-dimensional universe, every galaxy and every star, might be encoded on a two-dimensional surface at its boundary. The darkness within a black hole's event horizon is the ultimate hard drive, a perfect shadow teeming with locked-away data. We can see a parallel in the natural world. A tiny seed contains within its DNA the informational blueprint for a towering tree, a set of instructions that guides its growth from a hidden potential into a complex organism. In a similar way, the cosmos may have grown from an informational seed buried in the primordial dark. Its evolution not a random accident, but the execution of a deep computational code. The universe is not just expanding and cooling, it is computing itself into existence. This means that darkness is the fundamental medium, the substrate where information is written and stored. What we perceive as absence is actually the highest state of potential, a reservoir of unexpressed data waiting for the right conditions to manifest. Light and matter are the output, the visible result of processes occurring within the informational matrix of the dark. We are not just living in a universe of things, but within a universe of thought, a cosmic mind thinking itself into being through the dynamic interplay of presence and absence.